Hi there, welcome to Microlecture 41. We're going to be talking about solvolysis in SN1 and E1 reactions. SN1 or E1 reactions proceed through carbocation intermediates, and solvolysis is the key to the formation of a stable carbocation. You recall that when we were talking about SN2 and E2 reactions, we said we don't really want our solvent to be protic. We would prefer aprotic for those types of reactions. Here we're going to see why protic solvents actually help this other class of reactions, SN1 and E1, and at the same time we see why they would hinder the SN2 and E2 types of reactions. So first of all, the solvent type that you're going to see in your typical SN1 or E1 reaction is polar protic, meaning that there's going to be protons on our solvent. So other protic solvents would include CH3OH, CH3CH2OH. Okay, basically we're looking for OH groups, and then we know we have a proton sort of available in our solvent. And what these protic solvents do is they align around a positively charged species, like a carbocation, such that their delta negative oxygen atom sort of encapsulates or entraps the carbocation, stabilizing it. All these partial negative charges around a full positive charge on a carbocation is a stabilizing factor. And so that's going to lower the transition state energy for that intermediate. And if we think about what that might look like on an energy diagram curve, we'll take a look at that as well. That's going to cause the activation energy to be lower. It's going to speed up the rate of the reaction by lowering the activation energy. So solvent molecules that are protic encage a carbocation, stabilizing it, so that we can form it transiently before it goes on and reacts in a second step. So some details of the unimolecular types of reactions. So the one here means unimolecular. So both of these are going to be reactions that depend on only one species. So their rate limiting step is going to involve just one of the reactants. We would say rate equals the rate constant K times the concentration of our X or our alkyl halide or our R group that has a leaving group on it. Okay? Only the alkyl halide, we'll say or equivalent, just because it's not always an alkyl halide. Sometimes the leaving group is not a halide, is involved in the rate limiting step. So what we're going to find is that this mechanism depends on a couple of things. It's going to depend on the identity of the leaving group. Let's just compare some halogen leaving groups, and this isn't new to you. If you have a carbon to iodine bond, we know that the iodine atom is very large compared to the other halogen atoms, and so its longer, weaker bond is more easily broken, and so this is going to be the faster end of the spectrum. Okay, and then we have bonds to bromine and bonds to chlorine, and this would be the slowest. We typically don't see chloride ions being lost in SN1 or E1 reactions for that reason. Okay. And so typically what you're going to see is an iodine leaving group or a bromine leaving group because those bonds are longer, weaker, easier to break. The other thing that the reaction is going to depend on is the rate of substitution. And the rate of substitution matters around the leaving group, but in this example, we're going to talk about directly on the leaving group. So it turns out that tertiary sites for leaving groups where the carbon attached to the leaving group is attached to 3 other groups is going to be the most likely spot for a SN1 or E1 reaction to occur. Secondary sites where the carbon is attached to 2 R groups is the next most likely. And then we have primary leaving group sites. These reactions just don't happen. So the order is tertiary is faster than secondary. Primary is slower, but actually it doesn't even occur. So you'll see the reactivity parallels carbocation stability, with tertiary being the fastest rate because it forms the most stable carbocation. Okay, so let's do an example of an SN1 mechanism, kind of pushing the electrons around and then making sense of the reaction on an energy diagram curve. So here we have an alkyl bromide. It happens to have a double bond in it, but doesn't mean that we can't do an SN1 reaction. And we're going to see we have an alcohol. That's our solvent, and it's also going to be our nucleophile, we'll see. So what's going to form, first of all, is a mixture. Okay, we are going to see that this alcohol comes in and it attaches itself on the opposite face of the leaving group, but with equal likelihood, it comes on the same face. So we have to think about this and why that might be. Obviously, the mechanism is very different than that of an SN2 reaction, which proceeds through inversion only. All right, and so let's push some electrons around and see if we can't make sense of this. The way this mechanism will work is, first of all, we have what's called spontaneous unimolecular dissociation, which is just a fancy name for the leaving group just comes off of the molecule. And that can only happen if the conditions are such that we can stabilize the resulting structure, which is a carbocation. We took electron density away from the carbon atom when the leaving group popped off. So yeah, we also have the bromide anion sitting out here, but it's the organic structure that we want to keep track of here. And then what's going to happen is the alcohol is going to come in as a nucleophile, and it's not a strong nucleophile. It's very weak. We talked about that when we were discussing SN2 reactions and E2 reactions and the strength of the nucleophile or the strength of the base. There's no negative charge on the oxygen, and so we wouldn't consider this a strong base, and we also wouldn't consider it a very strong nucleophile. But the full positive charge on carbon, that carbocation, is what's going to drive this reaction. That carbon wants electrons a lot, and so the reaction proceeds. Oxygen's got a pair of electrons to donate to that very unstable carbocation. And so what we form there is another intermediate. Notice I drew this bracket at the beginning, and that means that this is an intermediate structure. It means you haven't formed the final product yet, and so everything that you form that's not a final product should be within this set of brackets. So I'm going to go ahead and draw the oxygen that just formed a bond to carbon. It still has a hydrogen atom on it, okay? Still has a lone pair of electrons. It still has an isopropyl group, and it's got a formal +1 charge, right? So then the last step is actually going to be to lose that +1 charge. And so after that intermediate forms, we go ahead and form either this structure or that structure, right? And again, that just happens by losing the proton. We could draw a mechanism for that by taking just a conjugate base in solution. In these polar protic solvents, you can always feel free to generate an equivalent of conjugate base for the purpose of deprotonating that product to give us the stable ether. In this case, the functional group that we form is an ether, right? And yes, it turns out that when the alcohol attacks the carbocation, being that the carbocation is a flat species, the alcohol can attack from either face. You can say top or bottom. And that is why we end up with the mixture that we do here of the possible stereochemistries. So thinking about what this all looks like on an energy diagram is important. Let's kind of trace the mechanism that we can see on this slide onto an energy diagram curve. And so we have reaction progress along the x-axis and energy increasing on the y-axis. And we're going to start at some particular energy, and that energy is going to correlate with that of the starting material. So I'll draw that starting material right there. The reaction is going to proceed so that the alcohol and the alkyl halide approach one another, and there's some sort of activation energy. There's some sort of transition state energy, which is the highest point here on this energy scale. And then we dip back down in energy to form the carbocation intermediate. And after that carbocation intermediate forms, the reaction proceeds to increase in energy. Again, we do form a second intermediate, and that intermediate is a little bit lower in energy. And then the conjugate base has to approach and react to deprotonate that alcohol to give rise to the final product, which has some sort of energy associated with it. Okay, so we've tracked through the entire reaction. We're seeing that there's two positively charged intermediates. The first one is a carbocation intermediate. The second one is a positively charged oxygen on our intermediate. And we have 3 transition state energies. We have transition state 1, transition state 2, transition state 3, and we have 2 intermediates. So this reaction is said to be stepwise, as opposed to an SN2 or E2 reaction where everything kind of happens all at once, the energy increases and then falls back down to our final product energy. That type of reaction would be concerted or all in one step. Okay, another thing I wanted to point out while we're here is that the activation energy for this first step allows us to see that that hump is like a lot larger to get up over than either of these other 2 activation energies. Okay, so that's telling us that activation energy number 1 in getting to the first transition state is our rate limiting step. So this, in the mechanism, losing the leaving group to form the carbocation is the rate limiting step. And so that's always what we're going to see. Okay, we're always going to see that the rate limiting step in any unimolecular reaction, so that's SN1 or E1, is going to be formation of the carbocation. And so that is why the original species here, the alkyl halide, is the only species involved in the rate equation. All right, let's compare everything we just thought about with regard to SN1. Let's compare that with E1 types of reactions. So I'll give an example of a reaction that it could occur through E1 reactivity. I have an iodine leaving group, a couple of other substituents, a couple of methyl groups on this structure. And that's just a weird way of writing methanol, right? So we sometimes, it looks like we're writing backwards because that's an OH group, but we're showing that the connectivity is between the oxygen and the carbon atom there. So that's why we write it that way. I could have written CH3OH as well, but you want to get used to seeing molecules written that way as well. And so what's going to form here is this alkene. All right, so I'll show you the mechanism. We are going to have spontaneous unimolecular dissociation. Again, fancy word for a leaving group just leaves. And that's going to result in the formation of a carbocation intermediate. So I'm going to put it in brackets because it's intermediate. This methyl group has gone nowhere, but I'm going to draw it flat now, planar. So on the line, not a dash or wedge, indicating that I know all three groups coming off of the positively charged carbon are all in the same plane because carbocations are flat. Of course, I still have this methyl group over here, so that needs to be drawn in. And then the next step is, since it's an elimination, I want to find a beta proton. All right, and so I'm going to draw in any beta protons, beta to the carbocation carbon. I mean, I have a couple here, but I have this one, and if I choose this one, then I end up with the resulting double bond. Okay, if I take that beta proton, kick the electrons in to form a carbon-carbon double bond, I end up with the more stable or more substituted carbon-carbon double bond. And so that's the one that is going to form. That is the hydrogen that's going to be taken in this reaction by our weak base methanol. All right, and so the resulting structure is just this, exactly what we have drawn up there. And so there's only actually one intermediate for this reaction. And so I can put my brackets like this. Okay, so let's give ourselves some room here to draw the energy diagram curve. Reaction progress along the x-axis, increasing energy along the y. And we've got the starting material, which just looks like this. It's an alkyl halide, and it has some sort of energy. We'll just say it starts at this energy. And of course, energy is going to increase as the carbocation forms. In other words, as the iodine starts to detach from the molecule. Okay, and then at some point, it's going to form like a stabilized intermediate. Okay, that's our carbocation right there. That is stabilized by the polar protic solvent system. All right, and so we have the carbocation intermediate right there, and then energy is going to increase and come back down again. And the actual ending energy is a bit higher because alkenes are less stable than alkyl halides. Alkenes, or carbon-carbon double bonds, are higher. Energy are more reactive than alkyl halides. So it's for that reason that I end up with a higher energy. But what's key here is that you have one intermediate. So that's the dip in energy in an energy diagram curve like this, and that you can pinpoint two transition states, transition state 1, transition state 2, and that you can find the activation energy for both steps, which look like this, and understand that transition state energy 1 has the higher activation energy, E sub A, associated with it, because that is the rate limiting step. And rate limiting step is, again, going to be the formation of the carbocation. Okay, so overall, the goals of this video and this microlecture are that you can identify the features of reactants that lead you to believe it's going to be SN1 or E1. And that involves noticing that you've got secondary or tertiary leaving group situations with very weak nucleophiles or weak bases like water or alcohols. And then the last thing that you want to remember is when you're predicting your products, we do expect mixtures, especially in SN1, where we end up with sort of a 50-50 mix of possible stereo configurations. Okay, so of R and S with equal likelihood. And again, that reason is because we form a carbocation flat intermediate. You think about what a carbocation looks like, as a flat species. So that's a carbocation in the plane of a paper. You've got an empty p orbital coming in and out of that plane. The incoming nucleophile can approach from either top face or bottom face. With equal likelihood.